I'm Dan. I am the project manager and kind of jack of all trades for our ML Ops team. And I'm going to present our movie recommender system, which is a production grade ML Ops pipeline built for real world deployment. So, first, let me walk you through the end to end architecture. We start with the data ingestion layer. We consume user events from Kafka Cloud, specifically the topics watch, rate, and recommendation requests. Um, our stream ingester validates schemas using Avro and persists hourly snapshots to AWS S3 as Parquet files. S3 version snapshots allow us to give exactly once semantics, meaning there are no duplicates, there's no data loss, and it gives us replay capability for retraining. It allows us to keep all that data so that we can retrain our model as often as we want. We train 4 different model types. Popularity is a baseline, item collaborative filtering, neural collaborative filtering, and alternating least squares. Out of those 4 models, the NCF model, the neural collaborative filtering model, certainly leads the pack at 13.7% hit rate at k equals 10. It's roughly 3 times better than popularity as a baseline, but it's also a deep neural network and it takes time and resources to train. So we actually went with the next best model for versioning, and that turned out to be alternating least squares, or ALS, and those serve recommendations through a fast API on AWS EC2 instance at around 35 milliseconds P50 latency. We built in support for hot model swaps for A/B testing and canary rollouts without restart. For monitoring, we use Prometheus to scrape all sorts of metrics, and we use Grafana to display those metrics as graphs and dashboards. We have Slack alerts set up to alert us immediately of any service level breaches. And in terms of CI/CD and retraining, we use GitHub Actions for orchestration. We retrain the models every Monday and Thursday, twice a week. And we have an automated testing pipeline with containerized deployments in multi-stage optimized Docker containers. Now let me hand it off to Arveen, who will take you through the live system.
Thanks, Dan. I'm Arveen, and I'm going to be walking through our data streaming infrastructure. Here's our Confluent Cloud cluster with 4 Kafka topics. We have myteam.watch for viewing events, myteam.rate for user ratings, myteam.reco requests for API probe requests, and myteam.reco responses for tracking recommendations served. You can see live messages flowing through, each with timestamps and user IDs. Our stream ingester consumes these events, validates them against Avro schemas, and writes hourly Parquet snapshots to MinIO. Here you can see our version data snapshots organized by date. This gives us reproducible training data and a complete audit trail. Every message is validated against our Avro schemas before processing. Invalid messages go to a dead letter queue, so we never lose data, but we also never train on corrupted inputs. Now, let me pass it to Lakshmi to show our trained models.
I'm Lakshminarayan HRD, and my role in this project is machine learning lead. Coming to the topic, we trained and evaluated 4 recommendation models on movie lens, which contains of 1 million of data. Our neural collaborative filtering model, it is the best performance with a hit rate of 10 of 0.137 and NTCZ of 0.067. It takes about 6 minutes to train, but gives us the highest quality recommendations. Here, ALS is the fastest model at 3 seconds training time with a good balance of quality and speed here. Uh, Let me show you the API live. I will request the recommendation for user 42. So you can see we get back 10 personalized movie recommendations with the model version and latency tracked. So in the screen, you can see that A/B test results for. So for experimentations, we implemented A/B testing with user ID model routing. So even users get the primary model or users get the canary. We use a two production G-test with a p-value threshold of 0.05 for statistical significance. So this is about this model, and my friend Krishal will now show our how CI/CD and on how it will got monitored. Thank you.
Hi, I'm Krushal, DevOps lead. Our CI/CD runs entirely on GitHub Actions with three workflows. CI.ml runs PyTest with 80% code coverage above our 70% threshold. CD.ml builds multi-stage Docker images and deploy to AWS ECS. Probes.ml hits our API every 15 minutes and logs to Kafka. Here's our Grafana SLO dashboard. You can see availability at 100%, P95 latency at 24 milliseconds, well under our 100 millisecond target. The request rate shows our probes traffic and health status is green. We also track data drift using population stability index and KL divergence. Current PSI for user feature is 0.005 and for item is 0.076, both under our 0.25 alert threshold. Our ECS cluster runs two tasks for high availability. The deployment uses optimized multi-stage Docker files, keeping our API image under 450 MB. Now back to Dan for provenance and security. Thank you.
Thanks, Kushal. Okay, so on security, our threat model covers Kafka injection, API rate abuse, and model poisoning attacks. Of course, we're using synthetic data because we don't have all these users using the system, but we need to be able to test it properly. And our anomaly detection flagged two suspicious accounts, one with over 100 rating events in a very short period of time, which is 17.6 times the average, and one with 50 rating events over that same period of time, which is about 8.8 times the average. Both exceeded our two standard deviation threshold, and we automatically quarantined that. So we also use Kafka SASL and SSL, API rate limiting, and schema validation as defense layers, but we don't have any robust security. We did identify two feedback loops in our system. First is known as a popularity echo chamber, which is where popular items get recommended more, which generates more watches, which amplifies their training signal. And the second feedback loop that we identified is it's called tail starvation, and that's where the bottom X% received zero exposure in our testing. These items never get recommended, so users never discover them and the model never learns to recommend them. And in terms of provenance, which is essentially the traceability of the whole system, we can demonstrate this using the same request that Lakshmi used as an example earlier for this user 545. We can see in the request response that in addition to the movie recommendations, we also get all of this provenance data. All we're going to take from it right now is the request ID, and we're going to go put the request ID in our trace endpoint and run that. And that returns all of this provenance metadata. The request ID, the timestamp, the model name that was used, the model version that was used, the git commit hash of the code that was trained, the code that trained this model, the data snapshot ID, which is the training data that was used to train that model, the container image digest, which is the hash of the Docker image that was running the API at the time. We get the latency, the user ID, the number of recommendations requested, the number of items that were actually returned, HTTP statuses. We were doing A/B testing at the time, so it tells us which variant was served out of A and B. The API endpoint that was called, the method that was used, and the Unix timestamp of when we just did this trace, which is a few seconds ago. Now, this provenance data lets you trace any prediction back to the exact model version training data, code commit, and container that produced it, which is critical for debugging and auditing and reproducing results in ML systems.